Hello and welcome to my research summary. My name is Christy Hazel and I'm currently a postdoc at UCLA in the mathematics department. In this video, I'm going to tell you a bit about my research area in algebraic topology and share with you a couple of my projects. So my research is in equivariant algebraic topology. So to set the stage here, let's let G be some fixed finite group. We're going to work in the world of G-top, so topological spaces that have an action, a continuous action by this group G. For example, if G was C2, the cyclic group of order 2, here are two examples of objects in this world of C2 top. So for example, on the left here, this is a genus 1 torus, where our C2 action is swapping the two halves of the torus. And these two blue circles are used to denote the fixed set. So these are the points that are not moved by the action. So in this world of G-top, the thing that's going to play the role of Rn, of our Euclidean space, is going to be these finite dimensional real G representations. And the thing that's going to play the role of our spheres is going to be our representation spheres. So SV here is used to denote the one-point compactification of this representation V. So we take our representation V and add a point at infinity. This gives us a sphere that inherits a nice action by our group G coming from the action on the representation. So in algebraic topology, we're often interested in studying different algebraic invariants. And we often want these algebraic invariants to come in the form of homology theories or cohomology theories. So recall a cohomology theory E is an assignment that takes each topological space X to a sequence of abelian groups En of X, one for each integer n. Furthermore, this assignment must satisfy some list of properties, one of which is that this must have a suspension isomorphism. So recall sigma k of X is used to denote the kth suspension of X, which is given by smashing X with the k-sphere. And the suspension isomorphism tells us that the reduced cohomology of the kth suspension of X should be given by shifting the reduced cohomology of X up by k. So in the previous slide, I told you these representation spheres, SV, are now going to play the role that our spheres did in usual non-equivariant topology. So in particular, we have this notion of equivariant suspensions. So sigma V of X is used to denote the Vth suspension of X, which is given by smashing X with SV. So now equivariant cohomology theories, this again is going to be some assignment that now takes to each object in our world of G-top, so each G space, and assigns it to some sequence of abelian groups. So now this is going to be graded on ROG, this representation ring for G, this Grothendieck group of finite dimensional real orthogonal G representations. And so one motivation for why this grading is kind of the right thing to do is that this lets us make sense of this suspension isomorphism. So now I can say that the reduced cohomology of the Vth suspension of X is given by taking the reduced cohomology of X and shifting it by V. A lot of my work has focused on this equivariant analog to singular cohomology called Bredon cohomology. And we denote this in the same way as singular cohomology. And when our group in question is just the trivial group, this really is just singular cohomology. And this M underlined here is just the equivariant analog of an abelian group, which is called a Mackey functor. I'm not going to give you the big definition of this, but the idea here is that this is really the data of H0 of a point. Just when we work equivariantly, we have different types of points coming from our different types of discrete G sets. And this M underline is the data of H0 of all of these different types of points and also the data of how they interact. So now I want to specialize to the case where G is C2, the cyclic group of order 2. So in this case, any C2 representation decomposes as a direct sum of copies of the one-dimensional trivial representation and the one-dimensional sign representation. Here I'm using this notation RPQ for the p-dimensional representation that has Q sign reps. So as this notation is suggesting, in this case, we can regard our Bredon cohomology as a bi-graded theory. Here, this first grading, P, is called the topological degree, and you can kind of think of this as the usual grading you're used to from singular cohomology. And then there's this extra grading around Q called the weight, that you can think of as this extra grading needed to help us keep track of stuff that's going on with the action. So a big question that motivates a lot of my research projects is just how much can we understand about this cohomology theory, this bi-graded cohomology theory? There are a lot of classical, beautiful results about singular cohomology. So how much of that can we kind of translate over here? Of course, that's a pretty big question. So we might specialize to say the constant Z2 or the constant Z Mackey functor. You can think of these as the analog of Z2 coefficients and Z coefficients for singular cohomology. And then we could specialize even more and just think about, say, C2 manifolds. So this is a pretty big question. So how do we kind of attack this? So first, we can do a bunch of computations. So we can compute the cohomology of lots of different families of C2 spaces. And then once we have these computations, try to come up with a geometric understanding of these answers that ideally can be generalized to other spaces or even other groups of equivariants. So this is kind of the big overview of what my research program tries to answer. In my last couple minutes, let me give you an example of one of my projects just to show you how this kind of plan of attack might go in practice. So one of my first big computations was looking at all closed surfaces with an action of C2. In 2016, Dan Duggar classified all C2 surfaces using equivariant surgery techniques. And using that classification, I was able to compute the Bredon cohomology of any C2 surface, first with constant Z2 coefficients and then with constant Z coefficients. I won't tell you the big answer in this video, but I'll just say that in both cases, I was able to kind of present the answer in a nice way that really only depended on a few simple invariants of the space. So this was my first kind of go do this big computation and try to organize the answer in a nice way. Once I had that answer, I really wanted to come up with a kind of geometric way to think about why the answer is what it is. One of the ways to do this non-equivariantly is to use fundamental classes of submanifolds. So whenever we have a manifold and submanifold, we get some special cohomology class in the cohomology of the big manifold associated to this submanifold. So I was able to replicate this kind of idea of fundamental classes in this equivariant setting, at least with Z2 coefficients. So I first proved a kind of weak version of the Thom isomorphism theorem. And then using these Thom classes that I was able to prove exist, I used these to then define fundamental classes of submanifolds. And this really worked for C2 manifolds of any dimension, not just surfaces. Tying this back to the surface computations, though, I was able to then show the cohomology of any C2 surface with constant Z2 coefficients is generated by these fundamental classes. So this gave a kind of very concrete geometric way to think about the answer, and it also made computing the ring structure much more accessible. So this is just one example of kind of following this plan of attack, computing the cohomology of surfaces, then coming up with these classes that kind of work for manifolds in any dimension, and then really going back to the surfaces and seeing these classes really do give me a good interpretation of that first answer. I'll just end with maybe mentioning a couple questions that still remain from this work. So one thing I'd like to still figure out is how much of this holds with Z coefficients, and also how much of this might hold with other groups. So thank you for listening. I have some other projects I'm working on too that you can read about in my research statement, or feel free to reach out and email me if you have any questions or want to hear any more about my work. So thank you so much for listening.